hopefully getting on to creating SSL certificates. One of the problems I encounter when speaking to developers is all the examples for IoT connecting to the cloud are typically unsecured. There's a lot of getting started tutorials, but there's very little information about how you use certificates to secure the communication between the device and the server, which increasingly is in the cloud. So what this workshop is meant to do is show you an end-to-end IoT solution. It uses very, very simple and very, very cheap hardware. It's about 10 euros, everything in the little pack I'm showing you there. But what it does is it's got a temperature, humidity sensor in. It reads that from the device, sends it to the cloud with a TLS SSL secure connection using both client-side and server-side certificates. So that gives you a nice secure channel. We then do some application in the cloud. We do a very simple calculation, but the idea is you could do some machine learning or predictive analytics to actually work out some values. And then we send a result back down to the device. And then that changes the color of the LED. So very simply, if I make this hotter by breathing on it, it reports every 10 seconds, so I've got to do this for about 15 seconds. So that means it's over 25 degrees. Humidity's already gone to 95%, and there we go. Oh. So there we go. I'm alive. My breath is about 32 degrees Celsius, so it works. So that's a very, very simple application. But what that's showing is that temperature going up to the cloud. The cloud's doing a very simple switch statement based on the temperature, and then sending back the color to turn the light. So that's the very simple purpose of the workshop, but it's the basis of more or less any IoT. Getting secure data up to a server, doing something on the server, and potentially sending commands back down to the IoT. So if you're in a robotics environment, that's sort of how they work in industry. You've got a server controlling, telling the robot what to do, and the robot then sends telemetry data or sensor data back saying what it's actually doing. So any sort of scenario around IoT, that's the basics for it. The part 4 of the workshop, we also show you how to get data into a Jupyter notebook, so a data science platform where you can then use Apache Spark or TensorFlow or any of the other machine learning or deep science engines to actually do some statistical analysis, machine learning, or deep statistics. So they're the 4 parts of the workshop. We're obviously not going to get through it this evening, but everything in the workshop is available within this Git repo. And we have had people go through this remotely. So hopefully we've now got the bugs out of the workshop and people can do it self-paced just using the material in the Git repo. So if you like what you're seeing, unfortunately I do have to take this hardware back because IBM doesn't give me a lot of money to go buy this stuff, unfortunately. But what I've done is, in the prereqs, I've actually given you all the search terms. If you put it into Amazon or eBay or your local supplier, you'll actually come up with the hardware. If you're willing to wait for it to come from China, you'll get it under 10 euros. If you get it locally, if it's equivalent to the UK, it's about 20 euros. So wait for 2 weeks, 3 weeks, get it shipped from China, and it'll be under 10 euros. So what we got, we've got the main board, which is the Node MCU board, and it's based around the ESP8266. It's a chip from Espressive, a Chinese company, and it was initially designed for adding Wi-Fi to other devices. So it started off as a Wi-Fi module.
So this Wi-Fi nano Arduino, right?
No, it's not an Arduino. It's not an Amtel device. It's an Espressive chip, but we can program it with Arduino.
Okay.
It's a different instruction set.
So we use Objective-C.
So you use Arduino, just like you would for a Nano, and you put a plug-in. Again, it's covered in the instructions to make it compile for the chipset. Okay. But unlike an Arduino, this has actually got 4 mega flash memory. So you can actually create a file system on here. So as you go through the workshop, we actually create a file system and upload the certificates onto the device. Normally, with an Arduino, you have to embed the certificates in code, create a binary buffer, and load the certificates in code. But with this, I can upload them to a file system. I can use part of that 4 meg as a file system, so the certificates stay on there. The other advantage of this board is it has Wi-Fi built in. So we looked yesterday, I can get one for £2.30. So about, pound's not very good at the minute, so it's about €2.50. That's what these cost from China, this board. It's 160 megahertz CPU. So it's reasonable performance. And as you've seen, we program it with Arduino. So that's the device. The sensor, I'm using a DHT11 here. If you want it more accurate, this is plus or minus 2 degrees Celsius. So it's reasonably accurate. If you're sort of measuring your garden greenhouse, it's probably okay. If you want it more accurate, there is another one called a DHT22, which costs twice as much, so about a whole €1.50, and that will give you to plus or minus half a degree of accuracy. So both work. And then this is a chainable red, green, blue LED, often known by NeoPixel, but it's a little package that has 3 separate LEDs in, a red, a green, and a blue one, and there's a little microprocessor in there. So I talk to the processor, and then the processor controls the LEDs. It's a very simple one-wire protocol that I can talk to, and I can make this go any color I want using the different values for the 3 different colors. So that's the hardware. Very, very simple and very, very cheap.
May I also ask something?
Yeah.
So the purpose of this seminar is to explain how to use your code with.
Yeah. So the idea with the whole workshop. So if you do all 4 parts, the idea is that you create an end-to-end IoT solution. And what I was doing tonight was just going to look at the first part of that workshop. So that's programming this, and if we got time, getting on to showing you how to create the certificates, and how to use the certificates to actually secure the communication. Because that's the bit that most developers struggle with, finding resources how to do that piece. So that's what we're about here tonight. How many people actually want to do hands-on and actually play with the devices? Yes.
Why you choose this board? Maybe you have another choice, Raspberry Pi Zero, maybe same price.
Yeah. The reason I chose this is I can't get anything with that performance, with Wi-Fi built in, for that price. Okay. There are some very good devices from Amtel, from Texas Instruments, from NatSemi. They're all 30 to 40 euros to give me that capability. So that's simply why I chose that device. It's cheap. The SD cards.
But there is possibility that you can use the Raspberry like OTG device. But okay.
Right. So the
price is reason.
yeah, the price is a reason. The other thing to be aware of when we're talking about things like Raspberry Pi and BeagleBones, they are single board computers. They run a high-level operating system like Linux. These devices, like an Arduino, are embedded devices where they don't run an operating system. So the code I write in the Arduino is all that runs on the CPU. There's no underlying operating system looking after the network, looking after multiple threads, looking after all of the memory and everything like that. I have to write everything in code for this device. So it is a low-level device. The advantage of it is I have total control of what goes on in here. So for example, to drive this one-wire protocol, I need very, very accurate timing, down to sort of the microsecond, because this is a one-wire protocol, so it's the length, the signal stays high versus low, signals whether it's a 1 or a 0. And these are very, very short times. On a Raspberry Pi, you sometimes have difficulty driving one-wire devices because you've got machine interrupts going on all the time that you can't actually control unless you write a kernel driver, which is not that trivial. So if you want to go hands-on, if you go to the Git repo, you can just start working through it. And then what I'm going to do is I'm just going to talk through what's in the workshop. So if you don't want to actually do it, if you just want to sit and watch, I'll explain how it all works, how it hangs together, and you can just sort of watch as I sort of go along through what's in the workshop. So how many people actually want to play along? Yeah, there's a few of you. Okay, so go to the Git repo. Have you all installed the software? I know you got sent out in advance. Great. It's only when I ask this question, everyone goes, no, didn't get around to it. So you've all got the software. What you can do is go to the first app, and that is just going to check that your environment works. You're just going to set up all the parameters, how to flash the device, and you're going to use an example sketch, which is just going to print out the details of what's on the chip. And that will then check that you've got everything. You can talk to the device, you can program the device. So for those watching, how many of you have actually used Arduino or programmed a small device before? Okay, some of you haven't, that's no problem. So one of the problems when you actually take a device like this, as I said, it doesn't have an operating system on. What I write has to run on the CPU. So one of the problems that you sometimes get is there's a very large learning curve just to run your first program, because you have to take care of how you boot the processor. So what you typically have to do is you have to say, wherever you start, I then have to go and set up a whole series of registers and interrupts to say what happens. I have to tell it where the memory is, what it can use for stack, what it can use for heap. So I have to set up all of these things before I can actually start doing any of the code I want to write. The advantage of Arduino is it takes all that away from you. When you create an Arduino program, I hope you can see that, you get this outline. And what happens when you run an Arduino program, it adds a lot of code under the covers to actually start the processor and get it running, get it all stable, and then it calls the setup function in your program. It calls that once, and then it calls the loop function, and it calls the loop function forever until you stop the device. So that's how an Arduino program works. Under the covers, they do all the work for you to get the device going, get it started, set up, get it established, and then that code will call setup. When that function finishes, forever, it's just going to keep calling loop. So that's how you write an Arduino program. it makes working with low-level hardware very, very simple. As you get more advanced, this becomes frustrating because you want to do more to set it up in a custom way. But to get started, you can't really get simpler than this. And then with the Arduino interface, you've basically got two buttons. One is compile and one is upload. If you look at some of the other tooling, you have so many options and it can be quite confusing just to learn how to use the tooling. But with Arduino, it is really simple. They call it verify, and that'll just compile your program and make sure that you haven't made any typing mistakes and it's invalid. And then you've got an upload button, and that will then send the application down the USB cable and into the device, and that will flash the device. When you're flashing the device, you're actually changing the program inside there. And the way it works is that sits in memory that survives restarts, and when it survives, you're taking the power out. So next time you turn it on, it will run the last thing you uploaded. So if I unplug this and then plug it in again, it's going to actually start where it left off and run that same program again. So that's how these devices work. So there we go. We got the green light back on. The other thing you get with Arduino is a very good set of examples. And what the workshop does is it takes you through a few of these examples. So the first one we look at is Wi-Fi Scan. Let me get rid of these so it's not as confusing. Right. So Wi-Fi Scan. And what this does is it just shows you how to start using the Wi-Fi interface. As I say, it's built in here. So first of all, we say open a link to the console. So whenever you run a program, you can bring up a window and you can get the program to send messages to this window. So that's one of the ways that you know the program's working. That's why you can just send debug stuff out, just so you can see what's going on. So if we look down the program, the first line says, open up the serial channel. If you're older like me, you remember modems where you had to get the speed right, the baud rate. So that 115200 is telling the serial link what speed to work at. And the important thing is that you get the monitor application, it has to match the same speed. If you don't match speed, then that's what happens. You get utter gibberish because it can't decipher the data stream coming down the wire. So they do have to be the same speed.
How could I know what speed should I use? Only to Google it, right?
So what you want to do is you want to do the fastest speed that works reliably. And 115200 is what the default is. And that's fast enough for a debug output.
For example, for normal communication with my device, I should use 9600.
That's really, really slow.
Yeah.
We were using that speed back in 1970. Devices have got a little bit better since then, and I would actually go up from there. Most devices will support 576 or 115200. So, yeah, I mean, 9600 is as slow as you can get. That's the basic for most things. But 115200, you can actually program these devices quicker if you've got a good USB cable, but that's a good speed. And then this is how easy it is to use the Wi-Fi. You just tell it that I want to use Wi-Fi. These things can actually be an access point. They are really powerful. They can actually be an access point, and they can connect to a Wi-Fi simultaneously. They can have two connections, one being an access point and one actually connecting to the local Wi-Fi. a common pattern is you get that to be an access point, you connect to that, it'll throw up a web page, and that's how you configure it. So a lot of devices where, I know a lot of routers do this, and a lot of IoT devices, when you get them, they say connect to the access point, it'll bring up a web page, and then you type in the values, hit go, and it'll configure it to get onto the local Wi-Fi and things like that. So this device can do that. So here I just want it to be a Wi-Fi station, which means connect to a Wi-Fi. And then all I want to do is say scan networks. It'll either tell me that there were no networks found, or it'll just print out the list of networks. So if I just upload this to my device, so you can see it's now compiling the sketch, and once it's compiled the program, it'll actually upload it. Yeah, this is slow. Oh. Oh. I've lost connectivity to it. Great example. It's crashed. There we go. Let's try again. So I just lost the connection to the port. So what I'm trying to show you, this is how easy it is to actually get a program up there. If you know a little bit of C, it's quite easy to do this. This is an example, so I didn't have to type anything for here. I just imported that. And a lot of the libraries will actually do this for you. They'll actually show you how to work everything. So here you can see it's actually uploading it now. I know orange on black is a terrible color combination to project, but you can't change that, unfortunately. And there we go. We're actually 100%. So if I open up the monitor now, you see it's starting looking for the network, and it's found 7 networks. So it's found the Fab Lab, it's found an Android and Eurome, EduRoam, and it's found 5 ESP devices. None of these should be access point modes. So I'm not quite sure what they are, but anyway, it's found 7 networks. And then because of the loop, it's just going to keep running that forever. So you'll see we delay 10 seconds. Every 10 seconds it's just going to scan the network and do this again. So then the workshop goes, and the guys who are working it will go through, and we're now going to show you how to look after the LED, how to get it to change color, and then how to control the humidity sensor. And then I'm just going to move on to part 2 and jump ahead of the guys that are actually going through, because this is really what we created this workshop for. So when IoT devices talk to the cloud, the protocol I'm using in this workshop is called MQTT. It's MQ Telemetry Transport. Has anybody used that before? Well, okay. So it is one of the more common IoT protocols to send data between a device and a server. It was invented quite a long time ago, and it was invented to really look after pipelines, where they had to use a satellite uplink to monitor remote pipelines, so oil and gas pipelines in Alaska and other fairly nasty places. But at the time, satellite communication was really expensive. You had to pay by the bit. So what they wanted was a protocol that had a very, very low overhead. So it was very, very efficient in terms of the data it actually put on the wire. IBM actually created MQTT, but we gave it to the open source community. It became an OASIS standard, and recently it was adopted as an ISO standard. So it's an ISO standard open source protocol that if you go to Azure, if you go to AWS, if you go to Google, on the IBM cloud, they have MQ connectivity with their IoT offerings. So it is quite sort of standard in terms of the connectivity option for IoT. And the way that MQTT works, it's a pub-sub messaging system. So if you're familiar with something like Twitter, where if I tweet something, I have no idea who's going to receive that. I don't really care who's going to receive that potentially. I just create my tweet and send it into the network. Anybody that's interested in me will subscribe to hear my tweets. So if I send them a tweet, they're going to get a notification that I sent something. And that's what pub-sub messaging is. The publisher will send data against a topic, but doesn't know who's going to receive that data. Anybody that wants to receive data from this will subscribe to the topic that this is going to send the data on.
It's locked somewhere on the server, right? So
Yeah. It will be persisted. Well, depending how you configure the server, it can be persisted. But that's how pub-sub works.
Yeah, for example, for marketing, yeah. So if we use some tool or app, so we can use it. Like
If marketing want the data, they subscribe to the data.
yeah.
So it's a simple pub-sub engine. So the producer of the data sends it or publishes it, and anybody that wants it subscribes to it. And when I publish it, anyone subscribing will get a copy of the message. So that's how the messaging works. And to secure it, we use the standard SSL, TLS technology that we use for the web. So MQTT can go over a TCP connection, and we then use SSL to secure that TCP connection. So how many people, you've all heard of SSL, but does anybody actually understand how it works? What it means when you say I've got an SSL connection, or what it means when I say I have an SSL certificate? Okay. So let me do a little bit of magic here. So to understand SSL, first of all, I need to teach you a little bit about cryptography. And then when we learn and understand how the cryptography works, you'll then be able to understand how the certificates work, and in turn, how the SSL handshake works. So to understand SSL, we need to understand two types of cryptography. The first one is something called asymmetric cryptography. And here I have a pair of keys. I'm no artist, but here you have a pair of keys. And they are created to work together. And the way they work is one key can encrypt data, but it can't decrypt the message. It can only encrypt a message. The second key needs to be used to decrypt the message encrypted with the first key. So that way you need both keys. Going back the other way, I can use that key to encrypt the message, but the only key that can decrypt it is the pair, the other key. And that's how they work. So the two keys work together. One of them will encrypt, the other is the only key that can decrypt, and I can go either way. The problem with this cryptography is it's very, very computationally expensive. It takes a lot of computing resource to run the algorithms to use these keys and encrypt and decrypt the data. So the other type of cryptography is symmetric cryptography. And here I have a single key, and that single key can both encrypt and decrypt. So I only need the one key, and that can both encrypt and decrypt the message. And the mathematics and the computing resources needed for this type of cryptography is significantly less than the asymmetric cryptography. So they're the basic types of cryptography that we talk about. The asymmetric is often called public key cryptography because one of the keys I mark as private and the other key is marked as public. And that means I keep the private one safe and only me will use it and be able to encrypt or decrypt with it. The public key I can give to everybody. Anybody that wants it can have my public key. And when they use that public key, they're fairly confident that they're talking to me, because the only person that could decrypt their messages is me. And when I encrypt a message, I'm the only person that could encrypt it if they decrypt it with that public key. So the asymmetric or public key cryptography means that you're fairly confident who you're talking to, because they have to own the private key. Whereas symmetric, if you have the key, you can both encrypt and decrypt a message. And this is often known as private key cryptography. So that's the first part of what you need to know about SSL. The second part is something called a certificate. Now, what a certificate is, it's just a collection of information. Depending what the certificate's used for, it may contain slightly different pieces of information, but they all work in the same way. So if I want to secure a server, what I will typically have is a start and an end timestamp. So the certificate is valid between these periods. And then what it'll also have is my sort of DNS credentials. So the server, what is the server address on the internet? So is it sort of IBM.com or is it fablab.sk or who is it? And then it'll contain other information like what cryptography it is used within the certificate. It'll contain information about who the certificate was issued to, the name of the company, what country they're from, what's their address, things like that. But what happens is all the information in that certificate is sent to a special function called a hashing function. And that function takes all that data and creates a key that represents all that data. And the special thing about the hash function is if I change anything within the certificate, it changes the hash number. And a good hash function won't allow me to manipulate it. So if I change a letter maybe at the top here, I can maybe change a letter at the bottom here to make it balance out. So a good hash function won't allow me to do that. So any change to the certificate will generate a different hash key. And then what I do is I take that hash key, I sign it with a private key, and I store that signature as part of the certificate. And then what that means is, if anybody has that certificate with the public key, which is often inside the certificate as well, they can do the same hash function and then compare it with the decrypted stored signature, and if they match, they know that no one's altered or tampered with the data in that certificate. What it also means is that I have to know who signed it, because their private key to generate that signature means I know who created that certificate. And obviously this is using asymmetric encryption to actually create that signature. So then you wonder, well, what's this got to do with SSL? So if you look in how the web works, so this is Firefox.
You have to switch the view.
Oh, sorry. That one. Yeah, so this is Firefox. And if I go and look at the preferences and then privacy and security, and then certificates, what you've got within your browser is a lot of public keys. But these are known as authorities. So these are people that can generate a certificate that we are meant to trust. And they have gone through a process where they promise to do a certain amount of checking before they issue a certificate. So if they issue a certificate, they have a very high certainty that who they're giving the certificate to is the correct person. So when you get your little security signature on your browser, it starts off by one of these trusted certificates authorities generating a certificate. And because you've got the public key here, you can then validate that the certificate that the server sends is a valid certificate. It'll also have the web address that it should be listening on, so you can check that to see, is the web address in the certificate who I'm actually talking to? So you then have a high degree of certainty that who you're talking to is correct because the certificate matches the URL, and the certificate was also signed by somebody who's done all the checks to say this person is IBM, or this person is Fab Lab, or this person is the company they say they are. So that's how certificates work. But what you often get with certificates is, rather than the certificate authority signing it directly, they create intermediates. So they create other certificates that can be used to sign, because they keep these root certificates very, very secure. So they'll often create another certificate and use that to sign the web server certificate. But if you start with the root certificate, you can then validate that's correct. That will then give you the public key to be able to check that the intermediate signatory, the intermediate certificate is correct, and then that will then allow you to check that the server certificate is correct. So you end up with chains of certificates, but you always start with the root authority, and then you can work along the chain saying, I can validate that, therefore I can trust it. I can validate that, which was signed by that one, so I can trust it, and I can validate the last one because it was signed by that one, which I can trust because it was signed by that one. So you end up with this chain of trust. So if we take those pieces, that is how we establish a secure connection using SSL. We use certificates to verify that the person at the other end is who we think they are, because they've got a certificate that was signed by a trusted person, and only they can have that private key. So we then know who we're talking to. The certificate will have things like the web server address, so nobody can be sitting in the middle and doing sort of like a man-in-the-middle attack. So that's how the SSL works. Very simply. So when we talk about SSL, there's a handshake that goes on when two things want to talk to each other. And it starts off with the client, which in our case is this. And that will say to the server, I want to establish a connection with you, and here are the security algorithms that I know about. Because when we look at the asymmetric, the symmetric, and the hashing functions, there are lots of different options, different levels of security, different levels of mathematical complexity and computing complexity needed. So I can say what algorithms I support. So a smaller device may not be able to use the longest keys, may not be able to actually do the most secure algorithms because they don't have enough computing resource. So the client will say to the server, these are the algorithms I know about. These are the it's called a cipher, which is a set of algorithms for symmetric, asymmetric, and hash. So the client will send a list and say, I know how to work with these. The server will look and say, can I work with any of those? And then it'll pick one of the client's ciphers that it can work with. And it'll send back, we're going to use this set of algorithms. The server will then send its certificate to the client. So the client's then going to check to see if it knows the root authority that sent that certificate. If it does, it'll then be able to validate the certificate signature. So the certificate has not been tampered with. And once it's done that, it can then look inside the certificate and say, is the certificate valid in date? Is it after the start time but before the expiry time? If so, then the certificate is in date. It'll then look at the web address within the certificate and say, is that who I'm talking to? If it is, it then says, okay, I now trust this certificate and the server is actually who I think I should be talking to. If the client has a certificate, it's then going to send its certificate to the server. And the server is going to do exactly the same thing. It's going to check to see, is the certificate valid? Do I have the root authority that signed the certificate? So can I verify it? And then look for the client identity within the signature. If the server likes the client certificate and the client likes the server certificate, then the client generates a little seed, a little bit of data that it encrypts with the server's public key and sends to the server. The server will then decrypt that and use that little bit of data to go through a function to generate a symmetric key. So the client who created that data will use the same function to generate a symmetric key. Then the client will send a message to the server encrypted with that symmetric key. The server will then see if it can decrypt it. It'll then send a result back to the client using that symmetric key. And then from then on, they're using symmetric, which is the cheaper algorithm, to actually talk. So that's what goes on every time you type HTTPS into your web browser. That little handshake goes on, where the client says, here's what I understand. The server says, this is what we're going to use. Here's my certificate. Usually your client doesn't have a certificate, but we are going to use one for these. So then the client will say, here's my certificate. We'll then generate a symmetric key, and then we start using that key after that. And that's how SSL works. And what we do in the workshop is we use a tool called OpenSSL. And I've given you all the commands here to generate the keys. Now, when you use the web, you've got no idea who your web browser is going to talk to. That's why we have these globally known root certificate authorities. But with IoT, you often have a very closed community of who's going to talk to who. So what I've used here is a self-signed certificate. So I haven't gone to one of the public root authorities because they want money. If you get a certificate from them, they want some money from you. So what I've done is I've said, well, I only want this to talk to my server. And my server is only going to talk to devices it knows about. So I don't need a public certificate that uses one of these public routes. Because all I need is my server and my client to know the root certificate. I don't care because nobody else has to talk to them. So as long as all my devices and my server share the same root certificate, it all works because they don't need a random stranger doesn't need to know the certificate. So that's why in the example we use a self-signed certificate. So the code we start with creates a root certificate authority, and a root certificate authority signs itself. There's nobody else to sign the certificate for it, so it signs itself. And we generate that root certificate.
This for IBM Cloud, right?
This is a root certificate. So this is a certificate that we're going to use to sign other certificates.
For example, this one mobile device or
It can be used for anything. I can create an email certificate from it. I can create a web server certificate. But the problem is, this isn't a public root certificate. So somebody needs to have that before they can communicate with me. But for an IoT device, that's okay. And what you can do on the IBM Cloud, and this also works if you set up your own MQTT broker. On Eclipse, there's a project called Mosquito, which allows you to set up your own server. But within the IBM Cloud, we can go into settings, and it allows me to upload, I'll make that a bit bigger, it allows me to upload certificate authority certificates. So the certificate I just created here, using these commands, I can upload here. And that will allow my server to understand the certificates that I generate. What I also do is I have to add the certificate, which we do down here, to the device. Because this device also needs to know that root certificate, because it's going to use it to verify the server certificate.
So the first one was like certification of device to the server. Now we are going to do.
So the first one was the certificate that's going to sign the certificate that's on the server and sign the certificate that's going to be on the client. That's our root certificate. We don't use that other than to check the other certificates. What we do then is generate a server key. And what we do is we ask it to be signed by the root certificate. So we generate a certificate, but we get it to be signed by our root certificate. And that's what step 3 here is doing. It's creating the private and public key for the server. It's then getting the certificate using that public key to be signed by the root key. And then we also update that to the IoT platform. So that's the root certificate, but then I can tell the messaging server to use that certificate that we generated in step 3. And when I add a certificate, I need to add 2 things. I need to add the certificate, but I also need to tell it the private key, because the server is going to use the private key to encrypt messages to the client. So I need to give it both the certificate and also the private key.
And how do you define them?
That is what's created with these commands. So these commands will use the OpenSSL toolkit to generate the key, and then we do something called, we create a certificate signing request.
Can you go through like by the all parts of the code? For example, the first one is the type of the SSL, right?
So this is
the encryption.
this is the asymmetric.
36.
Yeah, this is the asymmetric encryption algorithm that we're using in the certificate. We're going to embed a password, so nobody can actually use the certificate without typing the password, or the key without typing a password in. Obviously, because it's public, I use a very secure password. And then the output is going to be called this.
And this is what I mean.
And then this is going to create a new signing certificate request. And what we're saying is we want the certificate to last 3,560 days. So that's, 10 years.
Like valid, and after
It's going to be valid for 10 years, and then after that, I have to renew it and replace it everywhere. The subject just identifies who the certificate belongs to. Sorry. So all of this is just sort of saying who the certificate belongs to. And then we generate the certificate signing request at the end of it. And then with that certificate signing request, we're going to ask the tool to generate the certificate, taking all the information in that signing request, but we want it to be signed by the root certificate. And here I have to pass in the root certificate. Sorry, I'm pushing the wrong side of the mouse here. I'm signing the wrong place. We pass in the root certificate public key and the root certificate private key, which is there. And we have to tell it the password that we added when we created the root certificate. And that's then going to create me my certificate. Now what I'd normally do is I'd normally send this off to one of those certificate authorities. So I send the CSR file off to the certificate authority. They'll sign it, they'll take my money, and they'll give me a certificate that I can use publicly. But because I don't care about that, I can use my private, my own certificate authority to actually do the signing.
If I want to do not fixed passport, but to put it by a human, how can I type it?
Yeah, if you leave it off there, it'll prompt you on the command line.
So it can be like blank, or
yeah. If I don't put it, if I didn't put that in there, if I just missed that off, then when I type that line in, it would prompt me for the password.
Yeah. For example, if I want to go through mobile, it will prompt. Yeah.
Well, that's only just to create the certificate. Just that. Yeah, it'll ask me for the password. So yeah. The reason I do this is because I suggest people put this in a file because they never type it right on the command line. So I tell them to put it in a file and then just run it, and then it just works. And the last thing that this does, which is this one, is it converts the certificate. There are two different forms that a certificate is often put in. One is a text format, which is base64 encoded, and the other is a binary format. The text formats usually have a .pem extension, where the binary formats usually have a DER extension. Different libraries want this certificate in different formats. So for example, the library I use on here wants it in the binary format, so you have to put a DER on here. If I use a Raspberry Pi, a lot of the libraries on there will ask for a PEM format. So I've just included that last line so you get it in both formats. And then this last one is actually quite useful because if I'm on a small device that doesn't have a file system, that line will generate me a header file with the certificate embedded as a variable. It'll generate that automatically for me. So if I'm on something like Arduino, where I don't have a flash file system, I have to embed the certificate as a variable in the code, and that line will do it for me. The unfortunate thing is, for all users using Windows, that command doesn't exist on Windows. If you use the Linux subsystem for Windows, I point that out in the prerequisites. If you actually put that on, you end up running a Linux distribution within Windows, and then you do get that command, because you get a Linux command line. But on Windows, you don't get that command. So
the XXC command is a part of OpenCL?
No, it's part of.
C compiler?
I don't know which package it comes from, but it's on Mac, it's on Linux, it's just always there. But on Windows, it's not. But for this workshop, you don't need it. I just put it there, so you've got it if you need to move to a different platform. But for this, we don't need it. So once you've generated the server certificate, we're then going to add it to the IoT platform. And once you've done that, you can actually use the OpenSSL command line. I'm going to stand over this way so I hit the right side of the button. To actually ask the server. So this would be my server's address. And I can ask the server, show me the certificate you're using. So I can use that command line to actually go and check that the server's given me a valid certificate. So if you're not sure, if you want to have a look at a website certificate, I mean, you can do it on here. If you just click the padlock on any website and say show certificate, it'll actually show you all the details. So this is GitHub's, and you can go and get the details and see who created it, who issued it. So you can see that they use digicert.com to do their certificate. And you can actually go get all the information around what's in the certificate. But if it's not a web server, you can actually use this OpenSSL command to actually go and get the certificate and have a look at it. So then the next piece is we have to get the certificate onto the ESP device. And this is another nice thing about this board, is because there's a plugin to the Arduino IDE which allows me to generate a file system. So anything that I have in the data, if I create a data directory wherever I save the Arduino sketch, anything that's inside that data directory I can get sent to this device as a file system. So that's the source file for the code for the Arduino program. So I just create a data directory, and then I'm going to put my root certificate, and then I'm actually going to put the device public and private key in there. And then when I just run this tool, what it does is it creates me the representation of the file system and then sends it to the device. When I can actually use the configuration to say how big I want that file system. So when I switch to using the ESP board, I get this menu option. And this says there's 4 meg of memory on the device. I can have a 1, 2, or 3 megabyte file system. So how much of that 4 meg do I want to use as a file system? By default, we just leave it at 1 because we're only going to put 3 certificates on, and they are less than 2.5, they're about 2.5K. So I don't need a lot of memory. But that's how easy it is to actually create the flash file system, because the tooling will do it all for you. Within the code, I can then go and just bring up the code. I can then just go and use a library to read that file system. So I've got my certificate files with hash defines up at the top here, just the name of the files. So root, CA certificate there, and then there's the private key and public key. So I then say open the file as read only, check I opened it okay, and then I can just load it. And that allows me to read the certificates off the file system. So it's very, very simple to actually get the certificates in code. If I didn't have that, if we look at the .h files that were generated, they look something like this. Is that too small for you to read? So you can see it's actually created the root certificate DER file, and it's just given me it as a big array of unsigned bytes that are C-char type. So that's what that XXD command does. It just gives you that header file with the certificate in it like that.
You generated?
Sorry?
This certificate you generated?
Yeah, so that was the XXD command that was in the... So what I do, and what I recommend you do until you get really good at this, is I created come on, where is it? There, certificate SH. So because these are really, really long lines to type, and every time I've done this workshop, at least I would say 5 to 10% have typed stuff in wrong when doing this, which means their certificates don't work. And when you say to them, you have to go and regenerate the certificates because you've made a mistake somewhere, their face just drops because they spent like half an hour typing all of this stuff in. So, and for those that are working along, cut and paste all those instructions into a text file. If you're on Windows, call it .bat. If you're on Linux or Mac, call it .sh and make it executable. Then do all the modifications in this text file. And then if you get it wrong, you can go and fix it up and run it again. And you're just going to change whatever you got wrong. If you type every line out, every time you need to regenerate it, it's 20 minutes of typing. This isn't the securest way of doing it, but we're not running a secure, this is for you to learn. It's not for you to run a production system. So this workshop is for you to learn. So that's what I would suggest you do when you're creating certificates. Put it in a file, make that file executable or runnable, and then you can edit everything in an editor. Get it all right, make sure it's right. Yeah, because yesterday, we did this workshop yesterday in IBM, and someone decided they didn't like using password 123, and they mistyped the password in different places. They didn't use find replace, they actually typed it over and then mistyped it, and then it didn't work. So that's what I would suggest you do. Okay, so that gets us to the end of part 2, where we've added certificates to the device and to the server, and they've all got the root certificate. There's one other gotcha when you're using the IBM Cloud. There's this nice little panel that you can look at, and it's not working because I flashed that with the other program. So let me just start that running again. And this should start running. There's a nice little panel in here where I can see what's happening to my device. So this is the IoT platform console within the IBM Cloud. And you can see that I've got my device, which is here. And if it's connected, I'm going to get a little green light there. Let's get rid of that. So it's just uploading it now. So when it actually comes in and connects, I'm going to get a nice little green light there. And then when it's connected, I can also ask to see all the data coming from that device, which is a really good way of just checking if everything's working, or messages going as I think they should be going. So we're just uploading it now, so any minute now. That will finish uploading. There we go. So it's uploading, so coming through. It's now trying to connect to the network. It's got a network. It's read the certificates. One thing that you may have picked up, we checked to see the certificates in date. These things don't have a clock in them. So what the program does is it goes out and uses a network time protocol to go and get the time from the internet. So that's what you can see there. It's actually syncing time from the internet. And then it validates, is the certificate in date, which is what we get, certificate matches. So now I'm actually getting data, and you'll see my IoT console has come to life. I've got a green dot, means it's connected, and you can see the data that I'm actually sending. So every 10 seconds, I'm sending data. So as I sort of change this, there you go, you can see the temperature's gone up and the humidity's gone up. So that's live data. But this is actually using a TCP socket from the browser. And that socket is secured with the SSL certificate that's in the server. So to get this to work, you have to add the certificate, the root certificate that we're using on the server to my browser. Because otherwise that socket will say, I don't recognize who signed this certificate, so I'm not going to talk to you. And the problem with browsers is, depending on what browser it is and what operating system you're running on, they all look for different places for certificates. So Firefox has its own certificates internally. If I'm on Chrome, it uses the operating certificates if it's on a Mac, but it has its own certificates if it's on Linux. So you have to really understand where your browser is getting the certificates from, and then you have to add your root certificate to that store. If you're on a Mac, Safari uses the operating system. So all you have to do is double-click the certificate on the file system, and it will open up the Mac keychain tool, and then you just add it to the roots there. So that's the last bit about certificates. And then what you'll see is all the way through, I give you code as we build up the example. You've got the code as it should look at the end of this point, so you can actually check to make sure you've done the coding correctly.
And this is absolutely necessary to have all the certificates and trusted communication, or will it work also without it?
So I can
understand the importance, but it's necessary.
So, and if you go through the workshop, the first thing you do when we look at MQTT is you go to connection security and we turn it off. So then we get the MQTT working. We then just work with the SSL certificate, and then we add in the client certificate. So within the platform, I can choose what I want to allow my server to use. So what I'm using here is the client certificate and the password. So the client has to generate the SSL connection and then send a password over that connection to verify with the server. So that's the sort of most secure you can get, but you can choose what you want. You could use a password or a certificate, or you can just ask for an SSL, which is a server certificate only, no client certificates. So you can choose what you want. And most servers will allow you to do similar configuration things. They're doing a slightly different way, but you can usually use these options for that. So now that is sections 1 and 2 done. If you want to go and do sections 3 and 4 and you don't have devices, what the platform also has is a simulator. So if you go to the settings, you can look at device simulator, which is in data and devices here. If you turn it on, this little window pops up here. And this allows you to actually create a simulator for your device. It allows you to generate, to specify the format the data comes in, and it allows you to either have static values or provide a random value between a range. So I could say I want my temperature to be between 15 and 35. And then it'll pick a random value between 15 and 35 when it generates data. I can also say how often I want the simulator to generate data. So I can say 20 every minute. So that's going to give me every 3 seconds. Or I can actually say how often I want it to actually create the data. I can actually generate multiple schedules per device. So I can get it to say, send normal data for 10 minutes and then send an anomalous value, an out of range value, once every sort of 10 minutes, make it random between normal but include some external data. So with this, you can actually then go and do parts 3 and 4 of the workshop without actually having a device connected, because this will then generate the data that is coming in from the real device. Yeah, so this is what the actual device, real device is sending. And if you look at the workshop material, if you come into the root of the workshop, in English, there is a page under simulator which takes you through how to set up the simulator. So there, it actually takes you through everything you need to do to set up the simulator to simulate the device, including how to actually get the right data formats in. The one thing I will say though is don't leave the simulator running when you're not using it, especially if you haven't got a promo code. If you have your free account, there is a limit on the amount of messages you can send every month. If you have your simulator rattling data at a high rate, you can burn through that limit quickly. So if you've got a trial account, you do have more resource. But if you're on the light account, just be very careful and turn the simulator off when you don't need it. The other issue I've come into, which I think is still there, is you can't have certificates defined if you're using the simulator. So you have to take out your messaging certificate and put it back to use the default IBM certificate, because the simulator assumes that it's using those root certificates. But that's how you can actually then go on and do parts 3 and 4. So I'm just going to show you a little bit about what's in part 3 and part 4. Does anybody recognize this? Have you seen a screen like this before? No? Okay, so this is another open source technology. It's called Node-RED. And this is the quickest way to write an application. A lot of people, when they see this, think, I'm not a 5 anymore. I can write real code. But we've actually had meetings in IBM where someone's been talking about an idea, and in the meeting, someone's generated and implemented that idea, and at the end of the meeting, they said, you mean something like this. It's that quick. You can really build quite sophisticated applications in a couple of minutes.
How do you access it?
Yep, it's free. It's part of IBM Cloud. So when you actually deploy the IoT platform starter, which is what the instructions tell you to do, you actually get, so if I just go to the starter application, and I'm done, which is here. When you actually go in the starter, when you say visit, oh, I got the wrong one, doesn't matter. When you say visit URL, you actually get this editor come up, because this is the application that runs in the IoT starter. And just to show you what's going on, let me just turn that off So I get rid of these debug messages. Let me just show you how quick it is. So on the left-hand side here, you've got a palette of nodes. And you've also got a palette manager where you can install additional nodes. So you did robotics. So I don't know if you know things like the Johnny Robot library. You've got control for a Roomba, the automatic vacuum cleaner. So someone's hacked that, and I can now control it with this node. A number of different robot things, so the Sphero BB-8. Someone's hacked that, I can control that using these nodes. So there's a lot of nodes out there. There's over 1,000 nodes that have been contributed because it's open source. But some of the nodes you get out of standard are things like this. So this is the IBM IoT platform. And I can say that I want to talk to the service that's part of my application. I want all device data in any format. And then this is a debug node, which just dumps whatever it receives over here. And I'm just going to show everything in the JSON object. So when I deploy that, I start getting messages coming. And if I hover over a message, you can see which debug node created it. So now you can see I'm actually getting my live data. 2 nodes. I'm getting live data over a secure connection from this device. You can't write that code quicker than that. To actually, on a server, to make a connection to an MQTT broker, create a secure connection to that broker, and then subscribe and pull data from that broker.
That's when this code is running on the server
This
side
code is running in the cloud.
the cloud?
This code is running in the cloud. So you can see I've got the JSON data there. You can also see the topic that is published against. Let me just go, and if I do that, it causes it to expand when it comes in again. You can see what device it's come from and the device ID. So you've got all this information. So if I just want to look at, say, the temperature, there's a number of nodes here where I can just pull this in, connect this up, and say that all I want is the payload to be coming in from message.payload.d.temp. So if we look here, this is payload.d.temp. So now if I connect a node to here and publish it, when the next one comes in, I've got my temperature, just as 24. So again, I can manipulate JSON very, very easily and very, very quickly.
Like the first one is reading and the second one is writing?
Nope. So the data is coming in here. It's coming along this connection where I'm just printing it out, which is here. And then this one, I'm just saying, from all of this data, I just really want the temperature value.
Okay, so it's still only reading.
Yeah. So this is just pulling out the temperature value and making it available here. If I want to chart that, there's a set of nodes that make a dashboard. So now I can go and get a gauge. And because I've now identified the number, just that number, I can now say that this gauge, I'm expecting values from 10 to 40. And it's now going to color it over those values. I can say maybe I actually want it to be red only if it's over 35, and amber only if it's over 30. Slightly different to what I've got there, but you can do the things. And then I can then say where I want it to be displayed. And then what I've actually done there is we've got this dashboard, And I think, I can't remember what tab 7. And that's the gauge I've just created. So with that one node, I've now got a live dashboard on the web. Come on. It seems to take ages. There you go, 29. Not quite 30, but 29. So there, I've actually created a live. Now, you tell me how long it would take you to code that. So that's Node-RED.
Can you share this dashboard?
Sorry?
Can you share this dashboard to?
It's on the web.
So you can pass the link and.
If you go to HTTPS, and now don't forget this is now also secured. If you go to HTTPS ESP82BI-ESP8266workshop.eu-gb.mybluemix.net, you'll see that dashboard. So it's live on the internet. I can also secure it if I want to. I haven't. It's open, but I could put basic authentication on very easily as well, just to make it password protected. But what you can see is you can also make multiple tabs. So if you see here, I've actually got a number of different tabs, and this is what comes in with the database. So for example, here, I'm taking the data coming in, and I'm actually putting it in a NoSQL database. So this data is now getting automatically pushed without writing a line of code to a database. So the data is coming in. I'm doing a little bit of formatting here. So I'm actually adding a timestamp, and I'm then just pulling out the temperature and the humidity. So I'm actually storing this JSON into a NoSQL database. I'm storing it twice. I don't know why, but for some reason I'm actually storing it twice. Yeah, same database, so there we go. And I'm actually just doing an insert. So that's going to the database. This is the code that's controlling the light. So here, I've actually just got a switch node, and that's just looking at that payload.d.temp, so the same thing that I pulled out on the other thing. And then what I'm saying is, if it's less than 0, it comes out a connection node, between 0 and 9, connection 2, and so on. And then you can see here, for each connection, I've got a little connection point. So then what I do is I just create the JSON document I want to send back down to the device, in which case it's just values for the red, green, and the blue LED. And then I send it back down to my device. And the way it knows what device to send it to is, because if you remember from my debug node, I include the device ID and the device type in what's coming in here. So that information flows all the way through here, there, and it's available for the output. So it's going to send the message to the device that I'm processing the data from. So this will work with 1 million devices. I could actually get, if I had 1 million of these, that bit of code would actually work with each one of them, getting the light color. Yeah, so I send the data to the device that sent me the data.
I have a question. How it is, like, you know, when you are sending, how it knows how to read the code, where to put it? It's like algorithmically finding and defining? Or?
No, so if you remember, I've written the code, this one, I've written the code to create that D, and then when we read it, I actually put the temperature and the humidity. So I've actually generated the structure, so I know what the structure is going to be, which is why when I go back onto the server, I know what to expect. If I didn't, I just print it out and have a look and see what it sent me.
But this program just sends the data to the IBM IoT platform, and then platform communicates
Yes.
with your bot.
Yes. Yes. So this sends a message to the platform, publish this message against a topic which this device is listening to.
So you can, for example, update this TSH file on your computer, upload to the server, and after send to the devices.
You can do that, yes. You could do that. But that shows you just how powerful this is. And when you're prototyping, you want to do proof of technology, you want to get things running quickly. It's worth investing a little bit of time into this. If you get into robotics, this also runs on Raspberry Pis. This is installed on Raspberry Pi. If you do the desktop install, if you look at, it used to be included in Raspbian, but Raspbian got too big, so they pruned a lot of stuff out, and they now have it in a menu as available packages. If you click it, it'll then install it. But this will run on a Raspberry Pi. And some of the things that you can do are then start looking at some of the cognitive services. So with this technology, I can actually do things like speech to text, text to speech, visual recognition. I can do translation, so I can translate from one language to another. And these nodes all link up to the IBM cloud services that you can deploy, and I can then access them from a Raspberry Pi. Or I can get the Raspberry Pi to talk to a server application, which will then talk to the services, and then send the answer back to the Raspberry Pi if I want a single connection to the Pi. Or I can just get the Pi directly to talk to the web services on the cloud. So if you're doing robotic projects and you're basing it on, you can't run Node-RED on here yet. We are looking at, you can run a little JavaScript on the ESP32, the slightly bigger one. So people are looking at being able to run on there, but Raspberry Pi, BeagleBone, those size of single board computers will run Node-RED. And then you can actually link them up with all of these services. So chatbots and any of the cognitive services. Watson Data Science, the Watson Studio makes your analytics available as REST APIs. So you can actually make them available via a REST API. And again, I can then just use an HTTP node, which I've got here, to make a REST API call. So it's very easy to integrate any web services. Most of the IBM ones have nodes, and I've noticed that there are AWS nodes, so S3 storage. There are nodes for that. Very easy, and it's open source. IBM created it, the technology, but we gave it to the JS Foundation, which is part of the Linux Foundation, and we gave it to them 2 years ago. And we've now got other contributors that are adding to the project.
Just to clarify, when I install Node-RED on my notebook, for
Yep.
example, will I have access to all those services, or?
So you can install the nodes, but you then have to go and deploy the service and link it with the service. So
Or should I use only the Node-RED application running on the IBM?
No, you can run Node-RED wherever you want. So if I just show you this, when you, let's start with Cloudant. So if I actually look at Cloudant here, when I use Node-RED on the cloud, it knows how to get access to the services. If I run it locally on my laptop or on a Raspberry Pi, I have to create credentials. So here I can go through and create the credentials and say, what do I want the credentials to be? And that's now created a credential, and I'd have to put that in the API call. So this is a credential that I've now created, and you can see that I've got a password, and this is the host, the API key. So these are the credentials that I'd have to pass. And if I look at the...
So you can run your code locally,
Yeah.
and just connect.
So if I look
But
at,
services.
sorry, the Cloudant node, which is down here, when I connect to it, I can say an external service, and now it's going to ask me for that those credentials, the host, username and password, which I get from, which I generated here. So you have to deploy the service on an instance of the service on the cloud, then you can get the credentials and you can talk and just add them to the node on a Raspberry Pi. The nice thing about using IBM Cloud is a lot of the nodes that we've created, I can just say use the service that's linked to the Node-RED application, and then all the credentials get sorted out for you. Makes it a little bit easier, but certainly you can use all the services across a lot of devices. So that is Node-RED. As I say, you can create these dashboards. We've also got another one here where you can actually update the interval that the device reports. So this is going to send a message back to the device, and instead of 10 seconds, I can change that. So that's another option that we've actually got in the workshop. I'm going to finish off very, very quickly now. I'm not going to take you through this, but just to show you part 4 is showing you how to get data into a Jupyter Notebook. So how many people do data science or have used a Jupyter Notebook? Okay, that's good because I'm no expert, I have to be honest. Like you, I'm a device programmer. I'm more comfortable at this end than with data science. But increasingly important is what you do with the data. It's no good having IoT devices which just capture lots of data. Where the value comes is what you do with that data. And that's where a data scientist comes in. They take the data, they run it through all sorts of algorithms, they use machine learning to predict future behavior. They can do deep analytics to look at patterns within the data and work out how to extract value from the data. So what part 4 does, it just shows you how to get data from that NoSQL database that we're storing all the data in using the Node-RED flow. It shows you how to get access to that data in the Watson Studio. And then once you've got the data in there, this is what Jupyter Notebooks look like. But you can then pull in some of the computation engines like the Apache Spark or the TensorFlow to actually start manipulating and doing the data science or machine learning over that data. So that's what part 4 does. And we've got workshops for data scientists that go into that in a lot more detail. But I get very sketchy when you get too far in that because I'm not a data scientist. So I'm going to stop there. I've covered a lot of information. I hope you sort of followed along. But this workshop is public Git. It's online all the time. I'm happy to take questions. If you tell me what the forum the video's on, if you've got questions on there, you can just ping them at me. I'm quite happy to answer and support people that are working along. But what we really did or talked about, and what hopefully you maybe started looking at, is how to program the device using the Arduino IDE, how to get it onto the network, how to read the sensor, how to control the LED. Then we looked at how to get that talking to the IBM IoT platform. We start unsecured, then we add the server-side SSL certificate. We then add the client-side SSL certificate. That gives us a nice secure connection where we can also authenticate that there's no man-in-the-middle attack, because we can verify that the server we're talking to is who we think we're talking to, because only that server will have the private key and be able to decrypt our messages. We then looked at the back-end application, and that is a topic in its own right. If you've not seen Node-RED before, I really recommend you go look at it. You can't write code quicker. When I run hackathons, I have a little bet. If anybody can write code quicker than I can create in Node-RED, I'll buy them beer. If it's the other way around, they have to buy me beer. I've yet to buy a beer for anybody taking up that challenge. So look at Node-RED. Raspberry Pis, laptops running on the cloud. And then finally, getting data into the sensor platform, data science platform. So I hope you found tonight useful. I hope I haven't totally confused you. I invite you to go work through the workshop. Unfortunately, I do have to take these back with me tonight, but for €10, it's a great little board to play with. Great for little projects. And you don't have to worry about blowing them up, because at €2 or €3, it's not going to break the bank when you actually connect them wrong and they get very hot and start smoking. Any questions?
I do actually a few.
Yep. Yep.
The first one, it's like a little bit off topic, but if you are speaking about IBM Cloud, I would like to know if we also can use it not only for text, but also for images.
MQTT can be used for images, but that's not the sweet spot. If you want to use images, REST API tend to be used to do images, where you'd put them on something like S3 storage or a storage solution. Images can be multiple megabytes or even gigabytes.
So we need to pay.
It's not about paying, it's about using the appropriate technology to actually get the data to the cloud. So yes, IBM has visual recognition. You can use Node-RED to do that visual recognition, but you'd use a REST API to talk to that service rather than the IoT platform and MQTT. But yeah, there's visual recognition in the IBM Cloud, so you can use images. You can even train the visual recognition. So you can start with an empty engine, and you can say, these 200 photographs represent what I'm looking for. These pictures aren't what I'm looking for, so you can teach it what it's meant to be recognizing. So it's quite a nice service, very easy to use. You don't need to be a deep mathematician.
Okay. Second question. I know how to compile and upload my code to my hardware.
Yep.